Good evening.
Hello.
I think we'll wait about 2 minutes for people to trickle in and then get started. That's okay. All right, everyone. I think we can get started. So welcome back from the hands-on session or from an extended lunch break. And before I introduce the next speaker, I wanted to point out that after this talk, we're going to have a wrap up for the whole summer school, as well as the awards from both the posters and the hands-on sessions. So everyone should stick around for that. It will not be too long. And then without further ado, I'd like to introduce Professor Shruti Puri, who's going to talk to us about quantum error correction. So Professor Puri earned her PhD in applied physics at Stanford in the Yamamoto group. And afterwards, she did a postdoc in Sherbrooke under Alexandre Blay, and then at Yale under Steve Girvin. And in 2020, I think, she started a group as an assistant professor at Yale University's Department of Applied Physics. And there she is doing research, most notably on bosonic error correction codes. So without further ado, Professor Puri, the floor is yours.
Hi, everybody. It's afternoon there, I guess, or wherever you are. Good morning, good afternoon, evening. I'm really happy to be here and tell you about quantum error correction. So my talk today is going to start with just, the basics of quantum error correction. Then I'll tell you a little bit about the surface codes, because I'm sure everybody wants to learn about that because Google, IBM, all these big companies are pursuing it. And then I'll tell you a little bit about bosonic error correction. So I would like to have a lot of questions during the talk. My aim is not to go through all of my slides. I don't care if I don't go through all of them. I would rather have you understand what we're doing. So the beginning of the talk is going to be quite basic, and then slowly we'll build up the pace and the difficulty level. So at any point in time, so I guess you guys are going to post your questions in some chat, and then I'll stop frequently to answer those questions. Okay. So firstly, the part one will be about regular, qubit-based quantum error correction and surface codes, and then we'll go on to bosonic qubits and bosonic error corrections in part two. So when we think about errors in a quantum system, we can decompose errors. Like if you just think about single qubit error, we can decompose it as Pauli errors. So you can think about X-type error, which basically is the action of a Pauli X operator on your state. So 0 goes to 1, 1 goes to 0. You can have a Z-type error, which basically flips the phase. So you just pick up this minus sign here. And Y error is like action of both X and Z operators. So you don't only flip the qubit, but also flip the phase. Of course, you can have continuous errors as well. And of course, this is just a single qubit example that I'm giving you, but you can have multi-qubit errors. But even those multi-qubit errors, you can decompose as some Pauli errors or some continuous rotations of qubits, etc. Okay, now, when we think about errors, most of the work in the field of quantum error correction assumes what is called as a depolarizing noise model, which assumes that all of these types of errors are equally likely. That's the probability of a Z error is the same as probability of an X error is the same as probability of a Y error. And you can justify with this sort of assumption, assuming that you have a qubit which couples isotropically with your environment, so you'd expect all of these errors to be equally likely. However, in many cases, one type of error can be more dominant than other errors, and this happens when your qubit couples asymmetrically with the environment. And we will look at an example of such a qubit later on. So we'll, in many cases, the qubit couples predominantly along the Z-axis of the Bloch sphere with the environment, in which case the probability of Z errors is more likely than the probability of X and Y errors. This happens in a lot of qubit platforms. This happens, for example, in superconducting fluxoniums. This also happens in some trapped ion systems and even quantum dot systems. So in such kind of systems, we don't only we have to define a total error rate, which is like the probability of Z error plus X error plus Y error. But we also have to define like a bias, which is basically saying how much more likely is a Z error compared to an X or a Y error. Now, what are the sort of error rates that we want to achieve to implement some useful quantum algorithm? So if you want to say factorize a 2000-bit number using Shor's factorizations, the total probability of error should be less than roughly 10 to the minus 12. And if you want to solve like a bigger problem, like finding the ground state of this molecule called FOMOCO, which is used here, you can't see it. I'm sorry if because of this thing here, I can't move it further down. But anyways, so if you want to find the ground state of this molecule FOMOCO, the error rate that you want to have in your system has to be less than 10 to the minus 16. The numbers that we have in our labs right now are between 10 to the minus 2 and 10 to the minus 3. So there are orders of magnitude difference that we need to make up for. So you can either wait for the experimentalists to reach these numbers, or you just make quantum error correcting codes to reach these numbers. And of course, you want to do the latter. So before we go to quantum error correction, let's think about classical error correction. Very simple way a classical error correction could work. So in classical information processing, you store information in bits, so it can be 0 or 1, and the errors can take you between 0 and 1. So you would think about correcting this classical bit of information just by what we call a classical repetition code, which is you just take several bits, and when all of those bits are in the state 0, you call that as a logical state 0. And if all of those bits are in the state 1, you call that as a logical state 1. Now, there are some bit flip errors. So suppose there are 2 bit flip errors. So here, this bit and this bit has flipped to 1, and this bit has flipped to 0. So now you can easily see that if I go measure each bit, and I see that if most of the bits are 0, then I know that very likely the starting state would have been all 0 state. And if most of the bits were 1, then the starting state should have been the all 1 state. And so in this way, in this case, what you do is you just measure each bit independently, take a majority vote of the outcome, and decide, whether you were more likely to start in the 0 state or the 1 state. And this is how your classical error correction works. Now, if you blindly copy this technique for quantum error corrections, in quantum error corrections, you want to protect an unknown superposition, an unknown quantum state, right? So if you just have a single qubit, then you want to protect an unknown superposition of the single qubit state. If you blindly copy this, then you would assume that you can just take 3 qubits and copy them, make each of them to be in the 0 plus, x0 plus y1 state. And then just repeat what you did in the classical error correction. But of course, we know because of the no cloning theorem, this copying of information is not allowed in quantum mechanics. Moreover, we can't even go and measure each qubit independently, because if we do that, we're going to collapse the state. And we will destroy these superpositions, and this is just a consequence of the measurement postulate. So we can't even directly measure your qubits. Moreover, we also have to think about continuous errors, right? We just don't have bit flips. We could have, a continuous rotation like e to the I theta x, right? So how does, because of the no cloning theorem, the measurement postulate, and the fact that we have continuous errors, can we have a quantum error correcting code? Well, of course we can have it. That's why I'm giving you a talk about it. So the simplest of a quantum error correcting code is the quantum repetition code. It's similar to the classical repetition code. Here, we don't copy information, but we redundantly encode it in some entangled state of a many qubit system. So this is an example of a 3-qubit repetition code. So if all the 3 qubits are in the state 0, we call it the logical state 0. If all the 3 qubits are in the state 1, we call it the logical state 1. So now the superposition state x0 plus y1, the logical superposition state, becomes this entangled state of the 3-qubit system, right? So we are encoding quantum information. We are encoding one qubit of quantum information in a larger Hilbert space of a 3-qubit system here, and we are encoding it in some entangled state of this larger of a higher dimensional system. Okay, so now the next problem was sorry, so before I continue, I should say that this is allowed. Here, you're not copying information, you're storing it in an entangled state, and you can easily, this operation is allowed under quantum mechanics. Okay, now the next thing is, how do you detect for errors? So this quantum repetition code can correct for bit flip errors. So for example, or like poly X errors. So suppose you started with this state and there was an X error or a bit flip error on the second qubit. So the state becomes what's shown here. Now you can't directly measure the qubits, right? Because that's going to collapse the state. So what you're going to do is you're going to detect whether an error happened or not by measuring correlations between the qubit. Note that if there was no errors, then the state of first two qubits is the same, and the state of the last two qubits is the same. But if there was an error, the state of the first two qubits is different, and the last two qubits is also different, right? So you're going to measure whether those pairs of qubits are same or not to detect if there was an error. So what you actually do is you measure ZZ correlation between the two qubits. So if there was no error, then if you measure ZZI and IZZ, then the measurement outcomes are going to be +1 in both the cases. This state is an eigenstate of the ZZI and IZZ operator with an eigenvalue of +1. So when you make a measurement, you don't do anything to the state and you get the measurement outcome +1. Now, if there was an error, so if the state was what's given here, then this state is actually a -1 eigenstate of these two operators. So when you make a measurement, you'll see that you'll get -1 outcomes in the two cases. Now, instead, if there was an error on the first qubit, the measurement outcomes will be like this. This state is still, this state is a +1 eigenstate of the IZZ operator, but it's a -1 eigenstate of the ZZI operator. And similarly, if there was an error on the last qubit, this would be the measurement outcomes, right? So if you go and measure these operators, and if you make a measurement outcome of +1, you know there was no error in the system. If you make a measurement outcome of, if you see a measurement outcome of -1, you know there was an X error on the second qubit, and then you can go and correct it. How do you correct it? You can just apply an X again, right? X square is identity, so you can go correct that. And if you see a measurement outcome like this, you again know there was an X error on the first qubit, and in this case, there was an X error on the last qubit. So this example is a 3-qubit repetition code which corrects for 1 bit flip error. If you have 2 bit flip errors, it cannot correct for it. In general, you can make an n-qubit repetition code which corrects for n-1/2 bit flip errors. Now, what is the failure probability here? Well, so in this particular example, as I said, this cannot detect for 2 or 3 qubit bit flips. So if the probability of a single bit flip error was px, then the probability that there was 2 bit flip errors is this guy here, 3 choose 2 px squared 1 minus px, and if the probability there was 3 bit flip errors is this guy here. So clearly this sum is going to be smaller than px for when px is small enough, right? So actually if px is less than 50%, then this guy is going to be smaller than px. So you win by doing making a 3-qubit quantum repetition code. Now in general, if you have a n-qubit repetition code, the probability of a logical error is roughly governed by this formula, n choose n+1/2, px to the power n+1/2. In case n is large, then this formula reduces to this guy over here. Clearly, if px is smaller than half, so that this factor is less than 1, by just making a bigger repetition code, that is by just increasing n, you will decrease your logical error rate. You can decrease your logical error rate arbitrarily small by increasing n as large as you want, right? So in this case, error correction is going to be successful if px is less than half or if px is less than 50%. So this quantity, 50%, is actually a very important quantity. It's called a threshold. In particular, it's called a code threshold in the sense that here I'm only assuming, here I'm assuming that I can measure these operators perfectly, and I'm all my measurement outcomes are correct, that they're faithful, and I can really trust my measurement outcomes. And the only errors are happening directly on these data qubits. So this quantity of 50% is called the code threshold. So the code threshold for the quantum repetition code is 50%. As long as you're below this error rate, you can just increase the size of your repetition code and reduce logical error rates arbitrarily small. And the operators that you measure to determine if there was an error or not are called as stabilizers.
Professor Puri, there's a question. Won't measuring the correlations destroy the superposition?
No, it won't, because these states are eigenstates of the these operators. So it's not going to both 0, 0, 0 and 1, 1, 1 are the +1 eigenstates of these two operators, and so measuring it, so the superposition, any superposition of those two states is also the +1 eigenstates of those operators. So you can measure them, and it's not going to collapse the state. And similarly for these qubit states here. And you can, so this is like a hand wavy argument, but we can make, there's a whole stabilizer formalism of quantum error correction. And if you want to do really proper mathematical analysis, you can learn that formalism. But I'm trying to give you a hand wavy explanation of why this actually works. Okay, I see that my video has frozen, but you can hear me, I guess.
Yeah.
Okay, good, fantastic.
Okay, there's one more question, actually, if that's okay.
Mm-hmm. Yeah.
Are there codes with higher threshold probabilities, or is this like an upper limit on most codes or below it?
I don't, so I think it's possible to be better than this threshold in the quantum case. I think you can break this 50% threshold. Yeah. Okay.
I guess we can discuss more in the break.
Yeah. Okay, then of course we also need to correct for continuous errors. By the way, when I say you can break the 50% threshold, I'm saying that it's for the code threshold, not circuit level noise or phenomenological noise thresholds, which are what we actually care about in practice. And I'm going to tell more about that later. Okay, so again, we also want to correct for continuous errors. So for example, the continuous error was, some rotation about one of the qubits rotates by some angle theta around the x-axis of the Bloch sphere. So the state becomes what's given here. So basically now you have a superposition of the case when you have no error and superposition of a case with the state which has one error. But this is still okay, because when you measure these stabilizers, you'll either get the measurement outcome of +1, +1, that is, you'll either project yourself onto the no error case, or in which case there was no error and you don't need to do any error correction, or you're going to project yourself onto the -1, +1 case, in which case you project yourself onto the situation where there was an error and where the error was. The error was on the first qubit and you can go back and correct it. So basically this act of measurement itself projects you onto no error or error subspaces, and you can go and correct it. So the statement being that if you can correct, so in general, you're going to have X, Y, Z errors. So if you can independently correct X, Y, and Z errors, you can correct for superpositions of those errors as well. So in this case, you could correct for X errors, so you can correct for no error, superpositions of no error plus an X error as well. Okay, so now let's look at the big picture of how a stabilizer quantum error correcting code works. So the idea is quite simple, and if you understand the quantum repetition code, you basically understand everything, which is that if you want to store a bit of quantum information, you need to store that in some entangled state of some high dimensional system. So you can take many physical qubits and use, you define your logical states and use which form your code space, which can be some highly entangled state of your of this many qubit system, and that forms your logical space or the code space. And there are going to be some errors, and that errors can take you. Those errors are going to be mostly local, and those errors are going to take you to some orthogonal error space. That is, what I mean is that the state that you get after the errors is orthogonal to the state that you began with. And then you define the code space and error space with respect to some set of operators called as the stabilizers. The code space is a +1 eigenstate of all of these stabilizers. These stabilizers, so the errors anti-commute with at least one of the stabilizers, so that if the error happens, then at least if you measure these stabilizers, then at least some of them will give you a measurement outcome of -1. Why? Because your errors, you have designed the errors to anti-commute with, or you have designed your stabilizers to anti-commute with the errors, right? So now if you go and measure your stabilizers, if all the stabilizer measurement outcomes was +1, then you know that there was no error. If some of them was -1, then you know that there was errors. And you can take all of this information. So the measurement outcomes for stabilizers are called as error syndromes. So you take all of these measurement outcomes, that is, you take all of these syndromes, decode them, decide what was the most likely error, where it happened, and go back and correct it and recover your state. In fact, in many cases, you don't actually have to recover. You don't have to apply a correction operation. You can just keep track of what error happened in your memory and in a classical memory somewhere, and you're fine with it. But in general, you can also apply some recovery operation and correct it. Okay. So here, up till now, this, the example of the quantum repetition code that I gave you, we only considered errors happening on the data qubits, right? I assume that everything else is perfect. But you see, I have to measure the stabilizers. I have to do some I have to do some gates. I have to do some measurements to measure these stabilizers. And those measurement outcomes can be faulty. And in fact, those measurement devices can introduce more errors into your system. Let's see how that can happen. Let's say you wanted to do a control NOT gate in your system. And this control NOT gate is actually a very important gate. It's used in many error correction codes to actually detect errors or to measure these stabilizers. So it's a 2-qubit gate, which basically says that if the first qubit is in the state 0, don't do anything to the second qubit. But if the first qubit is in the state 1, you flip the second qubit. Okay, so this is the diagrammatic representation of the control NOT gate. Okay, so now what happens if you have an X error in the control qubit? You can see how X propagates through this gate. That is, just do your commutation relations. And you will see that an X error gets converted to 2 X errors in your system. So the act of measurement, so if you use this CNOT gate to, say, measure your stabilizers, then this act can introduce more errors. It can spread errors in your circuit as well. So your quantum error correcting code not only needs to correct errors that's happening on the data qubits, but it has to correct errors that can happen anywhere in your system. If your quantum error correcting code can do that, then we say it's a fault-tolerant quantum error correcting code. And fortunately, we know that such codes exist. We can have codes which correct errors anywhere in the circuit. And we also have, like in classical case, we also have a fault tolerance threshold theorem for quantum error correcting codes, which says that as long as your error per time step or error per gate operation is below some constant value called the threshold, then your error correction is going to be successful, and you can arbitrarily decrease the error rate, perform arbitrarily long quantum computations by using this code, by just making a bigger code and suppressing the errors arbitrarily small. Okay, so I'm gonna stop here for a second, and before I go into the surface code, let me stop for a second and see if there are any questions. Nope, good.
Yeah, I don't see any right now.
Fantastic. Okay, super easy, right? So now let's look at the surface code, which is, as I said, one of the most popular error correcting codes out there. So in surface codes, you have, what you have is, so the quantum repetition code could correct for only one type of error. Surface code can correct for all X, Y, and Z type of error. So in surface codes, a logical qubit is formed by a 2D lattice of physical qubits. So this is a 2D lattice. The circles are your physical qubits. And this whole patch is actually forming a logical qubit. This is a D by D patch. And your logical operators are actually X acting on all the qubits along this edge here, and the logical Z operator is the Z acting on all the qubits along this edge over here. In fact, any string that connects the top edge to the bottom edge is a valid logical Z operator, and any string that connects the left edge to the right edge is a valid logical X operator. Now, the stabilizers for the surface code, there are two types of stabilizers. The first one is the X-type stabilizer, which is the action of poly X operators on the qubits around the blue plaquettes. And at the boundaries, you have two body X stabilizers. And then the Z stabilizers are 4 body Z operators acting on the qubits around the green plaquettes. So the X operators anti-commute, so the X stabilizers anti-commute with the Z and Y errors. So you can use that to detect Z and Y errors. The Z stabilizers anti-commute with the X and Y operators. So you can use that to correct for X and Y errors. So just to give you an example, if there was no error in your system and you went and measured all of these stabilizers, you would see that all of them, the stabilizer measurement outcomes for all of them was +1. If there was an X error on this qubit, then this anti-commutes with these green stabilizers, the Z-type stabilizers, and so you'll see them to be measured in the -1 state. Of course, you'll see that X operators shown in this green, so X here, X here, X here, X here, also gives that also gives you the same error syndrome. So it also anti-commutes with the same stabilizer. So if you're not careful, you might accidentally So if you're not careful, you might accidentally think that, maybe the error is happening where, these 4 X errors rather than a single X error. But you would not do that because when you make the decoder, you make it so that you recognize the more likely errors. And here, the more likely error is a single qubit X error rather than the 4 qubit X errors on those 4 qubits. Right, but you see, there's another error chain which actually gives you the same syndrome outcome. So for example, if you have X errors on these 3 qubits, X here, X here, X here, it also anti-commutes with the same stabilizers. But in this case, it's okay because an X here and 3 X's here are actually logically equivalent to each other. So even if your decoder accidentally thinks that these 3 X errors were what actually happened, you'll be fine. But you should not confuse between these 4 X errors and this single X error, because that actually, you see, if you join this line, that's actually a logical X operator. So if you confuse between those, you'll actually introduce a logical error into their system. So decoding the surface code is not trivial. Because of this fact that it's a non-degenerate code, many error patterns give you the same syndromes, and you have to be careful about deciding what was the most likely error and go back and correct it. And I'm going to tell you a little bit more about decoders shortly. Now, how do you actually measure these stabilizers? Well, what you'll do is you'll put an ancilla qubit or an auxiliary qubit at the center here. You'll prepare it in some state, for example, the plus state, and you will apply these C0 gates between the data qubits and the ancilla qubit, and then you'll measure the ancilla qubit out. So if the ancilla qubit was measured in the same state as it began with, then you know that the stabilizer was in the +1 state. But if it flipped its state, that is, if you measure this to be in the minus state, but you had prepared it in the plus state, then you know that the stabilizer was actually -1, and that's how you measure stabilizers. So the surface codes are very nice because you only need like a 2D interaction, so experimentalists like it. I'm not going to talk about how you do computations on the surface code, but all the gates can be done with just local interactions. Everything is in 2D. Also, more importantly, it boasts one of the largest thresholds at the circuit level. By what I mean is that if all of these circuit level threshold means that you can apply errors anywhere in your system. Your data qubits can be faulty, your ancilla qubits can be faulty, measurements can be faulty, the gates can be faulty. There's going to be propagation of errors through these CNOT gates. Taking into all of that into account, the threshold for the surface code is one of the largest. It's about 1%, much less than 50%, but well, it's still one of the largest thresholds. What this means is that if the physical error rate, per gate operation, for example, is P, then the logical error rate is related to P and P thresholds using this formula. And L is, sorry, I use a different notation here, but L is same as D. So if you have a D by D lattice, this should be D plus 1 over 2. Okay, so basically what it means is that if P is smaller than P threshold, then you can just make a bigger and bigger lattice and reach lower and lower logical error rates. Okay, so just to again give you an example, if you wanted to factorize a 2000-bit number, then you need to reach a target logical error rate of about 10 to the minus 12. So if you have a physical error rate of 0.1%, threshold is 1%, then you need about 529 qubits to reach this 529 data qubits. I've not counted the ancillas yet to reach this particular logical error rate. Now, if you're able to improve your qubits by a factor of 2, so you decrease P by a factor of 2, or if you're somehow able to increase the threshold by a factor of 2, then now for the same size lattice, you can reach a much lower logical error rate. So now you can use the same lattice to actually factor to find the ground state of this big molecule.
I think there are two questions on this slide.
Yeah.
One is, I think, notational. So the question reads, am I understanding correctly that we're representing data qubits in the middle of the colored squares and ancilla qubits at the white circles?
No, the data qubits are the white circles. I have not shown ancilla qubits here anywhere. Okay. So ancilla qubits are only shown here, but yes, in reality, when you make this, you'll have at the center of every of this plaquette, you'll have an ancilla qubit, and of course, you'll also have an ancilla qubit here to measure those two body stabilizers.
Okay, and the second, obviously currently the problem is using additional ancillary qubits in order to detect and correct quantum errors. Isn't it possible to avoid using such qubits for quantum error correction, for example, by employing a particular sequence of gates?
I'm not sure what you mean. I mean, you have to measure, you need to extract information about errors. And so for that, you need to measure the stabilizers. So there may be alternative approaches to measure stabilizers, but no, the one that people have found works the best is this. Maybe you have a better idea, and we should talk about that then.
Yeah. Ivan, if you want to clarify your question, maybe in the break, we can talk more about that.
Sure.
And there's one more. So surface code requires a large number of physical qubits for one logical qubit. What is the benefit as compared to Shor's 9-qubit code? So
Shor's 9-qubit code, I believe, is a first order code. So it can correct for 1, X, Y, and Z error. Yes. So this can correct for as many errors as you want. Just make a bigger and bigger lattice. So the more, so for example, in the Shor code, this formula will, it'll be like P over P threshold square or something like that. So you could concatenate a Shor code with itself and, use concatenation to just reduce errors, but concatenation is a very bad scheme, like it doesn't work. You waste a lot of overhead, and this is why people work with topological codes instead of concatenated codes.
Thanks. I think we're ready to move on then.
Okay. I hate that my screen video is frozen because I like to move my hands around when I talk, and you can't see that. But anyways, right. So there's actually also a deep, so if there's some condensed matter people in the audience, there's actually a very deep connection between quantum error correction and statistical mechanics. So here, I mean the topological quantum error correction codes and statistical mechanics. You can actually map the noise in your quantum code to some disorder in your StatMech system, classical StatMech system. The threshold in the code basically then corresponds to a phase transition. So if you, so in your StatMech system, you can transition, you can have phase transition between a disordered and ordered phase. So ordered phase is like when your quantum error correcting code is correctable, and disordered phase is like when it's uncorrectable. And the point of this phase transition is actually corresponds to the threshold of the quantum error correcting code. And optimal decoding, the optimal way to find out what error happened, what was the most likely error, and where it happened, that is actually equivalent to calculating the partition function in your StatMech model. And partition functions are actually very, very hard to calculate. It's like I can't remember the exact class, but it's like NP or Sharp-P hard, or one of these complexity classes. And so exact decoding, optimal decoding of these topological codes can be very, very hard. And so this 1% threshold that I'm quoting is actually with minimum weight perfect matching, which is not the optimal decoder. It's a suboptimal one, but it works pretty well, and it's fast. But if you want to learn more about this, this is a good reference. I mean, this was first shown in the original Kitaev, Dennis Kitaev, Preskill, Landau paper. But the more recent reference that I like is this paper. Okay. So now I want to tell you a little bit, some new activities that have happened in terms of surface code in the last few years. So the 1% threshold that I quoted for you is basically for depolarizing noise model. You assume all errors are equal likely. However, as I said, in many qubit platforms, this is not the case. In many qubit platforms, Z errors are more likely than X and Y errors. If you know that your noise is like this, or you know that your noise is biased, then you can actually tailor the surface code and improve its threshold. And this sort of new direction has, or this new type of surface codes have been developed by a group in Sydney. And so one of the first ones was the tailored surface code, in which what you do is, instead of measuring the X and Z stabilizers, you measure the X and Y stabilizers. Okay, just change the stabilizers. This is totally fine to do. Now, if your noise is Z biased, that is Z errors are more likely, then you get, you see that all of these 4 stabilizers will tell you, yes, I'm -1. Something went wrong here, I'm minus, all of us are -1. You can use this extra information to actually make this decoder much better. You can actually improve the performance of the surface code in this way. In particular, what you can show in this tailored surface code is that if you have pure Z errors, you don't have any X or Y errors, then the tailored surface code is actually a repetition code for a quantum repetition code. It's equivalent to a quantum repetition code, and so we know that its code threshold at least should be 50%. And this is what they showed in one of the first papers was. So here, x-axis is the bias, which is the ratio between the probability of Z errors and the probability of X and Y errors. So a bias of 0.5 in this definition means you have a depolarizing noise model, and a bias of infinity means that you have pure Z noise. And so they plot the threshold as a function of the bias, and you see that indeed, when you have pure Z noise, it is like a repetition code, and it does have a threshold of 50%. Again, this is code threshold. I'm applying errors only on the data qubits. And at the bottom here, the threshold is about, can't remember, like 16 or 18% or something like that, which is actually the threshold for the regular surface code. Now, of course, you can have errors elsewhere. So then the next step, what they did was apply errors on the measurements. So you allow the measurements to be faulty. You're still assuming that your stabilizer measurement circuit is perfect. You're only assuming errors on the data qubits and the final measurements. You're still not accounting for propagation of errors through your CNOT gates, for example. In this case, of course, the threshold decreases because now you have to correct for more, you have to correct for measurement errors as well. And in this case, the threshold is about 6% or something for infinite bias for pure Z noise. And again, this is equivalent to a regular surface code for depolarizing noise model. So this is pretty cool. So what it's saying is that if you know that your noise in your qubits is structured, it has asymmetric, then you can exploit that to improve the thresholds for the surface code. There's a more recent work was actually another kind of surface code, which is called the XZZX surface code. Here, all the stabilizers are the same kind. You have only one kind of stabilizer, which is XZZX, acting on all the 4 qubits around these blue buckets. Everything is XZZX. And in this case, what your syndrome extraction circuit is going to have 2 C0 gates and 2 control Z gates, but that's the only difference. Okay. In this case, again, if you have a Z error, so if you have pure Z noise, you will have syndromes. These 2 syndromes will light up. Similarly, if you have 2 Z errors, those 2 syndromes will light up, and you can actually do a little bit of very easy analysis to show that this also actually looks like a quantum repetition code for pure Z errors. Similarly, it also looks like a quantum repetition code for pure X errors. So if you have X bias noise or Z bias noise, or in fact Y bias noise, this is also a quantum repetition code for pure Y noise. In this case, the XZZX code will give you 50% code threshold. So this is, again, they have checked it. So again, this is a code threshold. And they see, a 50% threshold for large biases. Right, and this is, so here they're actually using, even with the suboptimal decoder, so they're not even using an optimal decoder, they use something called as minimum weight perfect matching, which is a suboptimal decoder. They're able to get like 50% thresholds. Now, again, for the phenomenological noise case, the threshold decreases, and here you get about 9.5%-ish threshold. So pretty good, right? Now, if you improve your thresholds from 1%, or sorry, not 1%, whatever, 4.5% to 9.5%. Okay, but what happens when you have circuit level noise? Okay, now you have to think about how errors propagate through the gates that you're going to do. Okay, let's see. So one of the gates that you do here is control Z gate, right? So if you wanted to do a control Z gate between 2 qubits, you would have you'll try to establish a ZZ kind of interaction between your data qubits and ancilla qubits. In this case, if there's a Z error, remember we're trying to correct for the noise channel where Z errors are more dominant than other errors. So if you have a Z error on the data qubits, then a Z error, you can do your commutation relationships and you show that a Z error on the data qubit propagates as a Z error on the data qubit, it doesn't change. A Z error on the ancilla qubit also propagates as a Z error on the ancilla qubit. So the dominant error, which was a Z error, remains a dominant error even after you do the gates. Okay, so your noise channel remains biased. You will not convert Z errors to X or Y errors, so you're not converting a dominant error to the less dominant error. So the noise channel of the control Z gate is also biased. Similarly, you can show that noise in preparation and measurements are actually trivially biased. You wanted to prepare your ancilla qubit in the plus or minus 1 state or measure that in the plus or minus 1 state. The only thing you could do, the only type of error that could have happened was you thought you were preparing the plus state, but you accidentally prepared the minus state, and that's a Z error. So that's again a trivially biased noise error. However, let's think about what happens when you do a control NOT gate. Now, if you wanted to do a control NOT gate between your data qubit and ancilla qubit, you would have to have some sort of an XZ interaction between the data and ancilla qubits. In this case, a Z error on the data qubit will actually propagate as a linear combination of Z errors and Y errors on the data qubit. So you have converted a Z error into a Y error. That means initially your noise channel was biased, but as soon as you did a control NOT gate, the dominant error got converted to the less dominant error, and your noise channel becomes unbiased. So the control NOT gate actually unbiases the noise channel. And that means that you would not expect as big of an improvement in the threshold, because even with the XZZX code, for example, because the noise channel is no longer biased. In fact, there is a no-go theorem, which was first conjectured in this paper by Alifers and Preskill, which said that native bias-preserving C0 gates are impossible in strictly 2-level systems. So if you have your qubit and it is just a strictly 2-level system, which is the definition of a qubit, then you cannot actually do a C0 gate without converting the more dominant errors into the less dominant errors. So then it seems that this XZZX code is not as useful. But fortunately, with bosonic qubits are not strictly two-level systems. They are continuous variable systems. You can break this, you can go around this no-go theorem with bosonic qubits. And in bosonic qubits, you can do a bias-preserving CNOT gate and therefore take full advantage of the XZZX code. So if we have time later, if you actually get to those slides, I'll show you an example of a bosonic qubit, and I'll show you how the XZZX code performs with that particular bosonic qubit. I think we have a question.
Yes, we do. Here it is. Aren't these anti-commutation properties part of how parity check works? The fact that a CNOT.
Yeah, but this is not. So parity check is basically for errors before, so suppose there was no error during the CNOT gate. If there was a Z error on the data qubit before the CNOT gate, that's so, right? So you want to detect whether there was an error on the data qubit. So you apply a Z error on the data qubit. So a Z error on the data qubit before the CNOT gate propagates as only Z errors. Z error on the data qubit before the gate propagate as a ZZ error on the ancilla and data qubit. And that is the parity check that you want to do, right? Because that a Z on the ancilla means that you will flip the state of the ancilla, and that's what you're trying to actually detect. The problem comes when you do Z errors during the gate, not in the beginning of the gate, not at the end of the gate, in the middle of the gate. If you have a Z error, that's the problem.
All right.
Those errors get converted to Y errors. That's the tricky part. If you could do a CNOT gate instantaneously, like, basically 0 time, then yeah, this won't be a problem, but you can't do that.
Okay, thank you. I also have a question. Aren't like transmon qubits not strictly two-level systems also? Not just...
Absolutely, yes, absolutely. So if you have a transmon, right, it's not strictly a two-level system. You have higher energy states. If you can somehow take advantage of that, you may be able to do a bias preserving gate. We haven't found that gate yet for transmons or fluxoniums, for that matter. Transmons are not strictly bias noise qubits. I mean, you could make them bias noise in some manner, but fluxonium is a more natural thing to think about. That being said, the bias noise bosonic qubit, which is the Kirkat qubit that if I get time, I'll talk about, is actually a pumped transmon. So in that, I'm actually dressing the transmon to make that bosonic qubit and then go around this no-go theorem.
Great. Yeah, I think
okay.
We're about halfway through our time also, so I don't know if there's a natural time for a break.
Yeah, we can. Let me just show you this slide, and then we can take a break. Because this will anyway. This is the end of the first part, anyways. So here, what we did was, this is a result from one of our recent papers. We simulated the XZZX code, assuming, say, you have a bias noise CNOT gate. I want to show you what difference does it make if you have a bias noise CNOT gate versus if you don't have a bias noise CNOT gate. So if you magically have a bias noise CNOT gate, then I use some error channel, which is basically given here. What I just say is that, I apply Z errors with some probability in the control Z gate. Everything else is smaller than that by some factor here, which in this plot I'm taking to be 100. The control X, again, I'm by hand, magically I'm applying only Z errors. Everything else is smaller by a factor of 100, and similarly for preparation and measurement errors. In this case, I plot the logical error rate as a function of the Z error, PZ, for different sizes of my XZZX lattice. So for example, this red line here is for the XZZ lattice of size 4 by 12. And this third line here just tells you how many times I'm making a measurement, how many times I'm measuring the stabilizer. So 4 by 12 by 12 means lattice of size 4 by 12 by making a measurement 12 times. And so all of these for these different, so so I plot the logical error rate for different lattices, and they all cross at one point, and that is actually the threshold, because you see below the threshold, you actually get lower error rates by increasing the size of your code. Above the threshold, by increasing the size of the code, you're actually making the errors worse, and that's the definition of the threshold. So the threshold is PZ equal to about 1%, which corresponds to a C0 error rate of about 2%. But the reason I'm showing the C0 gate is that's the problem gate. So just to give you a reference, at this point, the C0 gate failure is about 2%. Now, if I actually assume that I don't have the right C0 gate, I don't have a bias preserving C0 gate, I use the standard C0 gate, which so I can, analytically calculate what should be the noise channel of such a standard C0 gate, and you get, these terms with some wires possible in it as well. And then I plot the logical error rate and see a threshold of about 1.7%. So it does make a difference in the threshold. But you're going to tell me that, well, who cares about the threshold? I mean, it's only a small error change, right? 1.7% to 2.1% of threshold, who cares? It's so small. Well, a small change in the threshold makes a huge difference in the logical error rate. So here, if I assume the same size of the lattice, just to make sure as well, for each of these points, the failure rate of the biased noise CNOT gate versus the unbiased CNOT gate is the same. So the total failure rate of the two CNOT gates is the same. The only difference is that the way the errors are distributed. So here we see that for the same size lattice, for the same total error rate, you get almost an order of magnitude lower logical error rates if you have a biased noise CNOT gate versus if you don't. That's the difference. You can get much better logical error rates if you have a biased noise CNOT gate. So I'm going to stop here. I had another plot to show that a regular CSS code doesn't work as well. It actually does worse than even the XEZX code, even if you didn't have a biased noise CNOT gate. It actually even does worse than that. The point being, if you have a biased noise system, whether you have a biased noise CNOT gate or not, you should use the XEZX code and not the regular CSS surface code. So I'm going to stop here for a little bit of a break.
Great, thank you very much. So maybe we can rest for a few minutes and then some questions maybe build up and take those before moving on.
Yep.
See you all in a few minutes.
Maxwell?
Yeah.
I'm going to log out and log back in just to make sure that maybe my video starts over again.
Yes, yes.
Okay.
That's a good idea.
Okay, yeah. Okay, am I back? Yeah, I think I can see myself move.
Yes, you're back.
Share. I'm also gonna grab some water.
So would it be okay if we went through a few questions?
Actually, I just wanted to clarify something that I said earlier. I think somebody had asked about if it can be better than 50% the threshold. No, sorry, I got confused a little bit. No, so I think if you just have one kind of, if you just have poly errors and the poly error is Z-type, then you can't have better than 50% threshold, code threshold, I believe. I got confused with if it can beat hashing bound in some cases, the quantum code can't. But anyway, sorry. I just wanted to clarify that. Go ahead.
Yeah, thank you. Okay, so one question is, how does one relate the experimental fidelity characterization of a qubit to the circuit's required threshold?
So you're asking, can you, if you have 1% fidelity of your gate, then what does it mean for the threshold? That's a very good question with a complicated answer. When we calculate thresholds, we assume a certain noise model. You can code a threshold of, you can code a fidelity of your gate to be 1%, but the error channel of your gate can be very different than what we assumed when we calculated the threshold analytically, and that might change, the answer, right? So so for experimentalists, you should take the thresholds as a grain of salt, in the sense that when I say it's 1% threshold, I'm saying effectively that if you're like 10 times below it, you're fine. So even, if your thresholds are 0.1%, even if your error channel is, different than what I assume in my calculation, it's pretty much going to be fine, and you're going to be okay. It's right near the threshold it becomes a little bit uncertain about the errors. So for example, if you give me you tell me that the threshold, that the fidelity of your gate is 1%, I have no idea about what the structure of noise is. I could use, for example, my decoder, which thinks it's a depolarizing noise, but you have bias noise in your system. It's not going to work as well, right? I need, so when I code thresholds, there's some knowledge that I'm assuming, which is not completely given by this one number fidelity.
Yeah, thanks for that answer. Another question here is, are there correction codes that encode more than one logical qubit into a single cluster of physical qubits, similar to a classical Hamming code?
Sorry, can you repeat that?
Yeah, are there correction codes that encode more than one logical qubit into a single cluster of physical qubits, similar to a classical Hamming code?
Yes. So there's LDPC, quantum LDPC codes, and other codes which do much better in terms of number of logical qubits, number of physical qubits per logical qubit. Surface codes is if you restrict yourself to two-dimensional codes, that is, you just want to have nearest neighbor interactions, everything is 2D, then this is the only thing possible. But if you allow yourself to have longer range couplings and so on and so forth, then you can have other codes as well. But in many cases, we don't know the performance, how well those other codes perform, actually. It's very difficult to estimate those numbers.
Okay, great, thank you. Yeah, there are no more questions then. So if you're ready, we can move on, or whatever you prefer.
Yeah, okay. So in the second part of the talk, I wanted to introduce a little bit about CV bosonic qubits. We won't have a lot of time to go into this, but at least I want to give you a little bit of flavor. Okay, so what is a CV qubit? Well, a CV qubit is a qubit encoded in an oscillator, or you can think about it as a harmonic oscillator. So the Hamiltonian of a harmonic oscillator is shown here. You can basically think about it as this parabolic kind of potential with equally spaced energy levels, and that's where you you can write the energy states in terms of Fock states, of Fock state 0, 1, 2, 3, etc. And you can basically encode a qubit you can define a qubit subspace in many ways in a single oscillator, right? So you can call the Fock state 0 and Fock state 1 as logical qubit state 0 and qubit 1, or you could call the superposition of Fock state 0 and Fock state 4 as your qubit state 0 and Fock state 1 as a qubit state 1. And so there's just like infinite number of ways in which you can encode a single qubit in your harmonic oscillator. Firstly, why do I want to do this? Well, it turns out that in superconducting circuits, which is what I'm interested in superconducting circuits, it's easier to make oscillators or resonators or superconducting resonators to have much longer lifetime, than the lifetime of, say, a transmon. So you basically begin with something that has fewer errors in it. And secondly, by cleverly choosing the qubit subspace that you define, you can actually do some sort of direct error correction in the single oscillator itself, because you have this large dimensional Hilbert space, which was the first thing that you needed to make a quantum code. So if you choose the subspace correctly or cleverly, then you can do some direct local error correction and then therefore further decrease the logical error rate in this system. And there are several examples of these bosonic error correcting codes, the GKP code, CAT code, binomial codes, and a lot of these things. And maybe we'll talk about CAT and GKP code today. So let's very quickly look at how error correction in a single oscillator may look like. So up till now, we have looked at error correction with qubits, where you have many physical qubits, and we call one, some entangled state of these qubits as the logical qubit state. Here, it's the same thing. However, you can think about it as some non-classical state of your harmonic oscillator will now encode a single qubit. So instead of thinking about it as entangled states, think about it as non-classical states in an oscillator, which I'll be using to encode my qubit. Now, I designed my quantum code assuming some local errors. I can have 1 qubit, 2 qubit, 3 qubit poly errors in my system. And my error correcting code is basically designed to correct that. Here, I want to correct against low weight errors, which are the more common errors, such as single photon loss, A, single photon gain, A dagger, maybe pure dephasing, which means the frequency of my oscillator is fluctuating, which is A dagger A, and so on. So here, think about errors in terms of actions of these, functions of A's and A daggers, and you want to correct for, and the low weight functions are more likely, and that's the ones that you want to correct against. So again, in this case, just like the regular qubit code, you will have your non-classical state encoding your code space. You'll have errors, and they'll take you to an orthogonal error space. You will have some stabilizers, which will anti-commute with the errors. So you can measure those stabilizers and detect these errors and decode what error happened and go back and correct it, right? Okay. Now, how do you detect an error here? Like, how do you even prepare a non-classical state of your oscillator? If it's a harmonic oscillator, then all these states are separated by the same energy. So if you put one, so say you started with some, you put in one photon, your the Fock state 0 went to Fock state 1. Well, but the Fock state 1 can also go to Fock state 2, 2 can go to 3, and so on and so forth, right? Because it's a harmonic oscillator. So in order to control a qubit in an oscillator, in a harmonic oscillator, or in order to even prepare a qubit in a harmonic oscillator, you need to have some nonlinearity somewhere. And in superconducting circuits, this nonlinearity comes from the transmon or the Josephson junction. So from Andreas's talk, you must have learned that, the transmon or the Josephson junction is the qubit, and you use basically the resonators or cavities to control the state of the Josephson junction. Here I'm reversing it. I'm going to use the oscillator as the qubit and then use the transmon as the control element. Okay. Now, why do I care about bosonic qubits? Now, as I said, there are some errors that some level of error correction can be done directly on these qubits. Maybe for some qubits, you can't correct all errors. So what you do is, by performing either some local error correction, you start with a very good qubit. And then whatever is left over, the small amount of errors that you couldn't correct at the level of the single oscillator, in order to correct those errors, you just, think about this whole system as a single qubit, which now you're going to put in your surface code, for example. I'm giving you the example of surface code here, but you can concatenate this bosonic qubit with any other code that you want. But the idea now is that since I started with something better, because the performance of this qubit, because of some local error correction that I could do, with that I could reduce the numerator here. Therefore, with fewer resources, I'll be able to reach the same logical error rate because I started with something better. Now, the other question that we asked was, well, yes, I understand that I can change the numerator, but can I somehow change the denominator if I have a bosonic code? Can I change the threshold? And of course, the answer to that question is yes. With these QuickAdd qubits that I may get a chance to talk about today, these are bias noise qubits, and they have bias noise control Z gates. Sorry, they have bias noise control X gates. Using that with the XZX code, I can have an XZX code with a higher threshold. So I can change both the numerator and the denominator with using this bosonic qubits. And that's why we care about bosonic qubits. Okay, just to have a very quick introduction to what these qubits are, let's think about, start with coherent states. So coherent states are eigenstates of the photon annihilation operator. I think you have seen Wigner functions in earlier talks. So even if you don't know what a Wigner function is, it's okay, you don't have to know about it. But if you do know about it, then you know that the Wigner function of a coherent state alpha is just a blob at I equal to 0 or positioning. Sorry, so it's a blob at alpha in the phase space. And if you have a coherent state minus alpha, it's a blob at minus alpha in phase space. Here I'm assuming alpha to be real, therefore these blobs happen at the q equal to 0 or momentum equal to 0 axis. Of course, now quantum mechanically, I can have superpositions of these two states. So you have even superposition and odd superpositions. So the Wigner function of these guys are two blobs at plus and minus alpha. And then of course you get these interference fringes at the center, which tell you that it's a superposition state. For the even superposition state, the Wigner function at the center is positive, and for the odd superposition state, it's negative. And that's how you can use to recognize that you have an even superposition state or odd superposition state from just looking at the Wigner functions. You can also look at these states in the photon number basis. So you can plot the photon number distribution of this even superposition state, and you'll see that only even photon number states are going to be occupied. And in this odd superposition state, only the odd photon number states are going to be occupied. So therefore, these states are called the even parity states or the odd parity states because you just have even photon numbers or odd photon numbers in there. And from now on, I will use this cartoon Wigner functions to represent these states. You just have to look at the center here. The center being red is positive, even superposition. It's an even parity state. Center being blue, it's negative, odd parity state. Okay. Now I can change. In the phase space, I can rotate these cats. So now I can have alpha to be purely imaginary, and I still get cat states, and it's still an even parity state and an odd parity state. But this cat is different. The vertical cat is different than the horizontal cat. Okay, so now let's look at the cat code, which is the simple, one of the simplest low-level error correctable cat qubit you can get. So my qubit states are going to be superpositions of this horizontal cat and vertical cat. So this superposition gives one qubit, and if you plot what the qubit looks like or what that state looks like in the photon number basis, you'll see that only states which are multiples of so multiples of 4, so 0, 4, 8, etc., are going to be occupied. And for the other superposition state, you'll see that you'll have even photon states, but they're not multiples of 4, which will be occupied. So they have different supports. These two states have different supports on in the photon number basis, and they're orthogonal. And of course, you can then use it to encode a qubit. Okay. Now, in these cavities, the most likely source of error is photon loss, in particular, single photon loss, right? So you just lose one photon at a time from the cavity. So if you look at what happens if there's a 1 photon loss here, you'll see that, oh, maybe I should go. So basically, if you have 1 photon loss applied here, the Fock state 4 will go to Fock state 3, Fock state 8 will go to Fock state 7. Similarly, Fock state 2 will go to Fock state 1, and Fock state 6 will go to Fock state 5, and that's what happens. So photon loss from this state gives you this state, photon loss from this state gives you this state. The parity of these guys is odd. You have odd photon numbers. Your code space was even parity. You had even photon numbers. So basically, the stabilizer of the code is the parity operator, e to the I pi a dagger a. Can you see this part of the screen that I'm
Yes.
highlighting? Okay, good. Right. So basically, if you measure this operator, then you'll know whether you started in an even parity state, which was a code space, or you ended up in the odd parity state, which was the error space. So you can use this to detect errors and correct them as well. Of course, this is only a first order code in the sense that it can only correct for single photon loss. It cannot correct for 2 photon loss. If you lose 2 photons at a time, you will actually have a bit flip type of error. It also doesn't correct for like dephasing kind of errors as well. So this is like the lowest, one of the lowest order codes you can have. Okay. So one way to think about it, there was a question before, and we can think about this as like the Shor code. Like it can only correct for a restricted number of errors and not everything. Okay, so how do you actually, can you actually measure these parities? Can you measure whether an error happened or not in an experiment? And in superconducting circuits, yes, you can do it. So to measure this parity, again, what you need is a nonlinearity, and your nonlinearity again is your transmon qubit. So what you do is have this dispersive interaction between your cavity and the transmon qubit. So here, A and A dagger is a cavity, Z is the poly Z of your transmon qubit. Okay, now when you exponentiate this Hamiltonian, so you unitarily evolve under this Hamiltonian for a time of pi over 2 chi, then you can just do the math and you'll see the effective unitary that you get is like some sort of a C0 gate, but it's basically saying that if the cavity is in the +1 eigenstate of your stabilizer, which was the parity operator e to the I pi a dagger a, then don't do anything to the transmon. But if it's the oops, sorry, there should be a -1 over here. This is 1 plus s and this is 1 minus s. So if it's a -1 eigenstate of the stabilizer, then it should do a z operation on the qubit. So you can use this to measure stabilizers. I'm so sorry, this should be -1 minus s over here. Okay, and so this is how you can use a dispersive interaction with the transmon to measure the stabilizer of the cat code. And this can actually happen at a very fast rate because the duration for this gate depends on this dispersive interaction strength. And this dispersive interaction strength is much larger than the rate at which single photons are lost from the cavity. So you can do this, you can monitor photon losses really, really fast. Okay. And this was done in experiments. And, this was the first demonstration of break even in quantum error correction, not just bosonic, just regular quantum error correction compared to everything else. So I'll tell you what is the important graphs to look at here, or important lines to look at here. So basically, if you don't have so you could store information in just the Fock state of the cavity. So you can store the information in 0 and 1 Fock state of the cavity. In that case, the lifetime is about 287 microseconds, right? So that's like the bare sort of inverse kappa of your cavity in some sense. Okay. Now you make a cat code, and the size of alpha that they use was actually square root of 2. Now, if you just make the cat code but did not do any error correction on it, then the lifetime actually decreases because you're not doing any error correction. You have just put in more photons, and it's more likely that you lose photons from a bigger cat than a smaller cat. And so the lifetime actually decreases. That's the first hit that you're going to get of one, and the lifetime decreases to 147 microseconds. Then now you do error correction. Now you actually measure the stabilizers using your transmon and do error correction. And with this, and in this case, they were able to increase the lifetime to 318 microseconds. Okay, so you actually did something better. You actually did something useful with your error correction by measuring these stabilizers. right? Now you'll ask me, well, why limit, what limited yourself to 318 microseconds? Why not even go much, much higher? The problem happens, you can't go much higher because you're limited by how frequently you can monitor the stabilizers because of the transmon. And let me explain why. So you're doing this gate between your cat code and your transmon, right? If there's an X error in your transmon, you can do the math here, right? You can do this math and you'll see that an X error during this gate operation, again, during the gate operation, will propagate as a phase rotation of the cat in the cavity, in the resonator. And I told you this is an uncorrectable error. So an X error from the transmon back propagates during the gate to an uncorrectable phase rotation of the cat code. Therefore, you have to, so in this particular experiment, they had to balance the number of, they had to limit the number of times they could use the transmon to measure the parity or to measure the stabilizer of the cat code. Because if you do it too often, you'll just keep on, adding this error and make your cavity worse. If you do it very less frequently, then you will miss the photon jump. So they had to choose a balance. They had to optimize it so that there's a balance between extra errors that were added into the system versus the errors that you were able to correct. So that limited the lifetime that you could go up to. This is the problem with most of the quantum bosonic error correcting codes in superconducting cavities. The ancilla, the transmon is the bad part, and that sort of limits how well these codes can perform. Now we have proposals, we have ideas, and there's some even experimental work out there to remove this effect, this backpropagation of errors from transmon. In particular, we had this idea of using a bias noise qubit. Imagine if you have a bias noise qubit which doesn't have this X error, right? As simple as that. Use a bias noise qubit which doesn't have an X error, and therefore you will not have this backpropagation of errors. A Z error is not a problem. A Z error in the transmon is not a problem. It's the X error in the transmon. So just use a qubit which doesn't have an X error. Perfect. Of course, that's a simple intuition and which works, but the devil is in the details. So you have to work out whether it's actually possible, what are the other limitations that come in, blah, blah, blah. Anyways. And so what we have found is that actually a better thing to use as an ancilla is a bosonic KERCAT, which is a pumped transmon, but we will get to that eventually. Okay, so again, just to reiterate, you could not, there were some errors you could correct in the system. There were some errors that you could not correct in the system. You still need to correct the remaining errors. What is the point? You just put it concatenated in a surface code and then correct remaining errors. Hopefully you're going to reduce the overhead that you need because you had some level of error correction in the beginning. Okay. Now let's look at another CAT qubit, which is the GKP qubit. Now let's look at another bosonic qubit, which is a GKP qubit. We just looked at the CAT code, which was, superposition of 4 coherent states, alpha minus alpha, I alpha minus I alpha. You can think about GKP states as superposition of, I don't know, many coherent states. And so the cartoon Wigner functions of the 2 GKP states actually looks like this. And it turns out that any error in the cavity, you can model as some combination of displacement errors. So if you've done quantum optics a little bit, you know what a displacement error is. It's just moving your system in phase space by some amount. So if the errors are, any error can be decomposed into displacement errors, but if those displacement errors are small displacement errors, then it turns out that you can correct all the errors, bit flip phases, all the errors are correctable with a single GKP qubit. So you can just make a bigger and bigger GKP qubit and arbitrarily reduce the error rate if you have, small displacement errors. However, however, this is actually not realistic in many experimental platforms, in particular superconducting circuits. You don't actually have small displacement errors. There's a limit to how big of a CAT state you can make. Other experimental factors kick in, and introduce errors which are not small displacement errors. A very simple example is, again, you're going to use a transmon to even make these GKP states or monitor its stabilizers, and an X error in the transmon can actually propagate as a large displacement error in the GKP state, which then becomes uncorrectable. So that's a sort of a brief overview of where we stand with GKP qubits. These GKP qubits have been prepared and error correction has been performed with them in both trapped ions and superconducting circuits. I'm just giving you the reference of the superconducting circuits, but in trapped ions, this experiment was very, fantastic experiments were done in Jonathan Holmes' group. I think he might have shown some of those to you. And we are about to actually have a perspective article on quantum error correction and the GKP qubits come out soon. So keep an eye out for that, and you'll see more of what are the challenges with the GKP qubits and how we can actually make it useful for scalable quantum error correction. Okay, now I have a little bit of time left, so let me I'll wait for a second to see if there are questions, and then go to the last part of the talk.
So I don't see any questions.
Okay, good.
Yeah.
So the last part of the talk is my personal favorite bosonic qubit. It's called the Kerkat qubit. The GKP qubit and the CAT code were made in a harmonic oscillator. The Kerkat qubit is made in an anharmonic oscillator. You see the way we approached this was, we noticed that the problem is the transmon, right? Any error in the transmon is going to backpropagate on your system, and that's just going to cause problems. But then we realized that, well, the transmon is actually, or the Josephson junction is actually an anharmonic oscillator. Now, can we make a bosonic qubit in an anharmonic oscillator? Turns out the answer is yes. And just we do this by just driving that anharmonic oscillator in a certain way. We get a driven qubit, and that actually makes the whole system better. It becomes a better anharmonic bosonic qubit. And let me tell you how. So the Kerkat was actually first made, it was made in Michel Devray's lab by Alex and Nick. But it was made in a device called as a snail, which is not exactly a transmon. It's made with Josephson junctions, but you can think about it like a transmon. And you apply a drive at twice the resonance frequency of this object. And because of this element has 3-wave mixing and 4-wave mixing terms. The 4-wave mixing term is given over here. It's it's what we call the Kerr nonlinearity. And the 3-wave mixing term is actually hidden. I've not put it there. But what basically happens is that if you apply a drive at twice the resonance frequency, because of that 3-wave mixing term, you convert 2 photons in the drive. You convert 1 photon in the drive to 2 photons in the resonator. And therefore you get this 2-photon drive. So you're exchanging 2 photons at a time. Your cavity or your Josephson junction, I shouldn't call it a cavity anymore. Your Josephson junction or the snail object is exchanging 2 photons at a time with your classical drive, which gives you this 2-photon drive. This Hamiltonian is written in the rotating frame, the frame rotating at omega A, which is the resonance frequency of this object. The phase phi is just the phase of the drive with respect to some clock sitting in your system. So if your drive is in phase with the clock, phi is 0. Now, once you have this Hamiltonian, you can factorize it in this form. This is exact factorization. I haven't hidden anything here. And here alpha is square root of this guy over here, p over e to the I phi by k. Now you can immediately see that the 2 coherent states plus and minus alpha will be destroyed by this term. So those 2 coherent states are the degenerate eigenstates of the Hamiltonian, which means their even and odd superpositions, which are the CAT states, are also the degenerate eigenstates of the Hamiltonian. Okay, here I've made a mistake again here in writing the equation. This normalization factor is only approximately square root of 2. There's some exponentially small things which depend on alpha, which I've neglected to write, but just for convenience, okay? So lo and behold, we have created a system where the cat states are the degenerate eigenstates. I can use them, they're orthogonal, and I can use them to encode my qubit. I'm going to use the phase phi equal to 0 to define my qubit. But if you rotate the phase phi, so say the phase phi becomes pi over 2, then because of the square root factor here, your cats rotate in phase space by an angle pi over 4, right? So basically you have a continuous family of cat states in a single oscillator. And this fact that we have this continuous family of cat qubits in a single oscillator is what actually lets us do the bias preserving or the bias noise CNOT gate. I won't have the time to explain to you what the bias noise CNOT gate is. You can read our papers. Right now, just trust me that the bias noise CNOT gate exists. Okay, so this is our bosonic qubit. I'm going to define my qubit with the phase phi equal to 0. Just forget about the phase phi. It is only important when I do the control NOT gate. So this is the Bloch sphere of my qubit. I'm going to define the qubit with the cat states along the x-axis. So cat plus and cat minus states are along the x-axis. The superposition of these two states, which are approximately the coherent states, are along the z-axis, and then you have the other superposition state over here. In this Bloch sphere picture, the Pauli Z operator is essentially going to cause a flip between the C minus and C plus states. So Pauli Z is like parity flips, and the Pauli X is just going to put a phase between the C plus and C minus states. On the right-hand side here, I'm showing you the Hilbert space, the eigenspace structure of my oscillator, this driven oscillator, in the rotating frame. So the key cat plus and cat minus states are exactly orthogonal. I proved that to you with the factorization trick that I used previously. Of course, there are other states as well, but these other states are separated in energy from the cat states by some energy gap. In this picture, the energy gap is negative, right? Like these states appear below, and you might be really confused by that, but it's just due to the fact that current nonlinearity is negative for our for the transmons. So what it really means is that, you know, if you wanted to drive, so say you started in the cat plus state, and if you wanted to cause transitions between the cat plus and cat minus state, then you would apply a drive at the resonance frequency of the cavity. But if you wanted to go to one of these excited states, you'll have to apply a drive at a frequency which is smaller than the resonance frequency by some amount. This is exactly the same as a transmon. This is what you do in a transmon as well, except that now, in a transmon, these excited states are Fock state 2, Fock state 3, and so on, or you can call them as GEF levels and so on, but here they're something a little bit different. Okay. Now the speed at which I can do gates in the system depends on this nonlinearity. So the bigger the nonlinearity, the faster I can do the gates. And in this system, the gate speeds can be, 100 to 1,000 times faster than the typical decoherence times. Again, here, I don't need an external nonlinearity to prepare my qubit or do any gate operations on it. I have the nonlinearity, the current nonlinearity. I have that inherently in this in this bosonic system, and I can directly use that to do my gate operations, right? Because I already have this energy separation between my qubit subspace and the rest of the Hilbert space. So I can selectively drive my transitions in this qubit subspace without actually leaking out to anything else. This is the difference between the Kuryat qubit and the other bosonic qubits. This is inherently a nonlinear system, and I don't need an external nonlinearity to do anything. Okay. And an interesting feature here is that also this pairs of excited states actually become degenerate or quasi-degenerate. And this is actually what provides the bias noise nature in this qubits. Again, if you want to go into the details, I recommend that you look at one of our papers. Now, how do you prepare these cat states, right? I told you I don't need any external thing to prepare the cat states. Well, all I need is, say I start with my cavities in vacuum. Sorry, again, I shouldn't say cavity. I start with my snail or this nonlinear element in vacuum, and I slowly increase the amplitude of the 2-photon drive from 0 to some value. Then if I started in vacuum, then it'll adiabatically follow the drive and split and form the cat plus state. And if instead I had started in the fork state 1, then it'll adiabatically follow the drive, split to form the cat minus state. And this has to happen at a rate which is, it has to happen adiabatically, which means the initialization time has to be greater than inverse of the kernel linearity, because otherwise you'll leak to these higher energy states. And again, this is not some theorist mumbo jumbo. This has been demonstrated by this very fantastic experiments by Alex and Nick in Michel Devery's lab, and they were able to make the Kercat in so the snail in the first experiment had the nonlinearity about 6.7 megahertz, and the initialization time was 320 nanoseconds, and this is faster than the decoherence time in the system. Now I have some time. Okay, so I want to give you a hand-wavy intuitive explanation of why this is a bias noise qubit. Again, all the mathematical details, if you're interested in, you can find in our paper. What I want to show you is that this qubit couples preferentially along the z-axis of the Bloch sphere to the environment. Doing an X or a Y is going to be very hard. Okay. Firstly, to show that you can do z operation, what you can do is just what does a z operation do? A z operation just flips the C plus and C minus states, right? So just look at the matrix elements of C plus and C minus states for some operators. So any coupling with the Kercat qubit with the environment can be written in this form. A and A daggers are the Kercat modes, and the E is the some environmental operator, right? So now just sandwich this and look at the matrix elements of this of the A dagger M A N for the C plus and C minus states. And if M plus N is odd, then these matrix elements increases with the size of the cat, with the alpha. Which means that clearly you can have a coupling with the environment along the z-axis, and the strength of that coupling actually increases polynomially with the size of the cat. So yes, it can couple to the environment along the z-axis. Now I have to tell you that it doesn't couple to the environment along the x or y-axis. In order to do that, again, to get an intuitive picture, I'm going to look at the classical metapotential corresponding to this Hamiltonian. What that means is I just replace A and A dagger with complex number, like complex numbers, not operators anymore. So I just replace A and A dagger by x plus Iy and x minus Iy, and look at the potentials. Of course, I'm going to get a 2D potential, but I'm just showing you a plot, a cut along the y equal to 0 of that potential, and it actually looks like a double well. So classically, what it means is that you can have two stable states, minus alpha and plus alpha. These wells appear at minus alpha and plus alpha in phase space. Of course, quantum mechanically, we can have superpositions of these states, which are our cat states. Okay. Now, if I wanted to do a X operation, it means that I want to go from minus alpha to plus alpha and plus alpha to minus alpha. That means I'm going to go from the left side of the well to the right side and right side of the well to the left side. Well, this is actually very hard to do. You can't tunnel under the barrier. Tunneling under the barrier is exponentially suppressed due to this gap. The other thing you could do is jump over the barrier. But in order to jump over the barrier, you need a very, very, very high order coupling. You have to make many, 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 many jumps before you can go to the top and come back down. So again, going from left to right side of the well and vice versa is very, very hard in the system. And this is why we have a bias noise qubit, and you can show that the bias increases exponentially with the size of the cat. Okay. You can again read our paper. You can do all the gate operations that you need to do to have a universal fault-tolerant quantum computing in this architecture. Out of these operations, the initialization, the Z rotations, the readout, the control Z gates and the control X gates are the bias noise gates. The X pi over 2 rotation is actually unbiased. So in our quantum computing architecture, we will actually never do this gate on a data qubit. We will only do this gate on the Ancilla qubits, and that's okay to do. We can do that. That's allowed. So the interesting gate here is, of course, a C0 gate, which really differentiates this from something like a fluxonium, because you can do a bias preserving C0 gate here. Okay, so I'm gonna leave this part. I'm gonna show you the results very quickly from this paper, our most recent paper, where we actually imagined a XZZX surface code with these snail-based Kercat qubits, you can do everything in 2D architecture. You don't need anything 3D. And I'm going to show you quick results. So we again simulated the XEZX code. For our Kercats, we use different size of the Kercat. So this first plot is going to be for 1 photon Kercat. That means alpha of 1, which means it still has a bias, but it's a small bias. And what we do is we add some thermal photons to the system, and we calculate the threshold. So what we want to determine is what should be the, when you make the snail, when you design the snail, what should be the T1 time of the snail that you should aim for? Okay, that is equivalent to like in the earlier plots, I was threshold plots, my x-axis was PZ, probability of a Z error. Here, the x-axis could be probability of Z error, but more intuitive thing for us to do was look at it in terms of the T1 time of your snail, because that's what experimentalists care about, right? So here again, we looked at the XEZX code, looked at the threshold, and here we find the threshold to be, the kappa, the kappa is inverse of the T1 time. That divided by current nonlinearity should be this order of 10 to the minus 4. What it means is that if your current nonlinearity is about 10 megahertz, then you need a snail with a T1 time of 144 microsecond. And this corresponds to a CNOT gate fidelity of 3.1 microsecond. Sorry, 3.1%, what am I saying? Yeah. So your threshold for the CNOT gate is 3% here, which is the most noisy gate in the system. Everything else is actually much higher fidelity. But so if you have a T1 time of 144 microsecond and 1 photon cat, you're golden. Right now in the current experiment, the T1 time is about 15 microseconds. So you're about factor of 10 away, and we're not super satisfied with it. So let's make the size of the cat bigger to make it more biased. This increases the threshold. The threshold in terms of the CX gate infidelity is about 6.5%. So you may double the threshold. What it means in terms of this lifetime of the T1 time is that now you need a 64 microsecond T1. So it's better. We're getting closer to the 15 microseconds. In this work, we actually did not even optimize the gates. You can gates, I mean, you could do simple pulse shaping experiments to make the gates even faster. And it's we have given some arguments in our paper to show that this very, very easily, this threshold lifetime can be brought down to 32 microseconds, which I'm happy about. Ideally, I would like to bring it down to 15 microseconds, but well, I'll take 32 microseconds. Okay, so I'm going to stop here. That was the end of my talk. And basically the overall takeaway message is that firstly, think about how errors are distributed in your circuit. It's not just the total fidelity that matters, it's how the errors are distributed. And secondly, bosonic qubits are scalable. They can be much better. They have inherent properties which make them much better than regular qubits. So I'm going to stop here and take questions.
Great, thank you so much for that talk. I definitely learned stuff. And I guess while we wait for questions to trickle in, I wanted to ask if you're aware of other implementations of the bias CX gate that are out there.
So for example, in GKP qubits, you can do bias CX gates, but it has to be, it has to be a higher dimensional system. Again, you could imagine doing it in a fluxonium or transmon. I just don't know how right now.
And for other types of qubits, that's
like what?
Like maybe trapped ions, yeah.
I haven't thought about it. Again, I'm sure it's possible, but I don't know.
Okay, thanks.
There's other properties of the Kercat which make this much better. So I think that a bias noise, I don't know, but I kind of suspect that a bias noise GKP qubit won't do as good as the bias noise Kercat qubits because how the Z errors grow actually. So, you can increase the size of the cat and decrease the X or Y error rate, but you'll also increase the Z error rate. You might do that. And if the Z error rate increases too fast, then there's no way your error correction code can handle it, even if you don't have any X or Y errors. Just somehow it all works out well with the Kercat that everything grows or doesn't grow in the right way, and we still get a big advantage.
Okay, so Anya asks, sounds like bosonic qubits are more favorable regarding error correction. However, experimentally, most qubits are not bosonic, right? So is there a big movement to change to more bosonic qubits?
I would say yes. I personally know a lot of people who are now trying to think about this. Let's hope it, I mean, forgive anything else. Amazon is doing bosonic modes. There you go. That's the, if Jeff Bezos can put money in there. But no, so that there is a movement to go towards these qubits. I think there's a, I think until a few years back, there was the advantage of these qubits was not very clear, but I think research in the last few years has shown that it's really going to be better. So make it.
And that paper you're referring to, Anya, is Amazon put like 100-page long paper on the archive about how they're going to plan to scale this up and make it a thing.
Again, let me point out the difference. They're not using Kurgats, and I hope there's no Amazon person here, and I hope they don't watch this recorded video. But I personally don't find their proposal very intriguing or realistic in the sense. So they're using something called as dissipative cats, which are like Kurgats, but they're made in a different way. I just think that practically those are difficult to make, operate in the right regime, and scale up. So there's like two different schools, and the reason that they are doing dissipative cats rather than Kurgats is because they want to do I think they want to do phononic stuff as well. So it's hard to get the kernel linearity. But then they have something called as an ATS. If you look at their paper on the chip, they have this ATS, something called as an ATS on it, which is actually like a snail. So my argument is, if you have that, make a Kurgat. Why are you doing all this other stuff? But that's my personal thought. Maybe it'll change in a few years. I don't know.
Great, thanks. Good to get that. Another question. So from Ivan, many people start to think about autonomous quantum error correction. Do you think that it would be possible using bosonic qubits? Do you have any idea?
A great question. Yeah, I know. So I've been, with bosonic qubits, so for example, with GKP, if you look at the first GKP preparation paper in superconducting circuits in Michel's group, there they actually use autonomous error correction. So say the two ways you can do error correction, right? Like you can measure the stabilizers of your code, like you can measure the stabilizers of your GKP code, keep track of that in memory, because you can't, just by making one stabilizer measurement, you can't yet be sure of whether there was an error or not, right? Because there can be measurement errors. Your transpond can flip accidentally. So basically what you can do is keep all of that information in memory and do some sort of Bayesian estimate or something like that to determine what was the error. That's not what was actually done. So I call this like a measurement feedback kind of error correction, whereas the autonomous version is that irrespective of, I mean, you imagine that there's no errors on the transpond and you apply correction operation as if there was no measurement of error, which means that you might accidentally apply the wrong correction operation. So I think there's advantages and disadvantages to both. Of course, in the measurement feedback scheme, you may be more protected against measurement errors, but then you have to make more measurements, and maybe your classical FPGA, however you actually decide to decode it, it's not super fast. And in the other case, you're limited by, but in some sense, you are limited by, again, the measurement errors from the transpond. I think the jury is still out, because somebody has to sit down, actually look at the numbers and see in what regimes are these two cases going to win or lose against each other. I think certainly there are cases where this autonomous scheme will win. There are some other cases where your measurement feedback kind of thing is going to win. I just don't know which one will win when.
Great. It's all of the questions from the question and answer. So I guess with that, I'd like to thank you so much for sharing your expertise. It's really awesome. We can get you here to talk about this. And
great, thank you. I had fun, and thank you for all the nice questions.
Great. So I think we're going to transition into wrapping up this summer school. Professor Puri, you're actually the last talk. So I think, Uwe, if you're around, I'm going to flip it over to you for awards and last words.
I am around. Somehow my camera doesn't work. All right. Hi. Very nice talk. Thank you. I learned a lot. It's very motivating.
Thank you.
Yes, let me find the PowerPoint presentation. Okay, there. All right. So now we're just gonna end the summer school with telling you about how you get credits from the university for this, and revealing who won the poster awards. So the first quick thing, it's also in the leaflet that we sent to everyone, is if you write a report, it can be short, on one of the theoretical lectures, for example, the one from Professor Puri you just heard, and send it to us, or solve and comment the exercises from one of the tutorials with some detail, but like doesn't have to be a master thesis, until 1 month from now or 4 weeks from now, and send it to us in a PDF format with a subject exam to quantum.school@epfl.ch. We will give you a certificate, and if you're from EPFL and you've told us that you want credits for the school, then we already basically told EPFL to mark you to get credits if the report is sent in. If you happen to forget, one person asked, they forgot to sign up for the credits, we will give you a certificate, and then you can talk to your school's administrator or your program's administrator, and they will hopefully give you credits. From ETH, the physics department, I think, will give you 1 credit, and the department in EPFL will give you 2 credits. All right, that's easy. If you need an attendance certificate, for example, to justify time off work or something, you can also send us an email, and we'll give you a certificate that you've been attending the school. Although, I mean, I don't know how relevant it is since it's on Zoom, and yeah, anyway, but let us know. Then the material. So we asked all the professors for their slides, and Professor Puri, I would also appreciate if you could email us your slides. Will be uploaded to some place on the website that we will email to everyone, and then we will have a password that will tell you in the email, and so you can follow the or look again at the slides and check them out. You can also look at the recordings. They're still available on YouTube. The videos are easy to find on our channel with the link that you all got. And if you've got the link, you can search for Quantum Hardware and Software Summer School 2021, and you'll probably find them in YouTube. We'll also probably make the Zoom recordings available after cutting them a little bit to not have all the breaks in there and so on. All right, and now to the fun part, the poster awards. So we had a lot of interesting posters and good presentations, and we had 4 judges for the 2 poster sessions. Alexander Grimm, who was actually mentioned in this talk. If you paid attention, you saw his work on the Kirket. Giuseppe Carleo, Pascal Selina, and Florian Reiter for Wednesdays and Thursdays poster session. And each of them sent us 1 favorite and 1 runner-up. Luckily, none of the runner-ups and favorites aligned. So we have 4 winners and 4 runner-ups. How was it possible to win this competition? Basically, we sent the poster judges all the PDFs and all the abstracts before the school, and they looked at the posters and the abstracts and selected a couple, 5, 7 posters of their respective sessions to look at and to talk to the presenters. Then during the poster sessions on Wednesday and Thursday, they met the presenters and listened to the presentation, and then chose which one they liked best. And all of them said that the choice was very close. So then we met if you almost won. So then we already come to the runner-ups. First one was Ivan Roykov. He also asked a lot of very interesting questions. So good job on that from ETH Zurich, from Jonathan Holmes group. Yeah. Then Ali Caterini Grazia for quantum perceptron and quantum neural network structures with a teacher-student scheme. Third one, Ekaterina Altavil for vertical integrated circuit QED architectures for semi-superconducting devices, also from ETH. And finally, Charles Mull for direct classical microwave optical transduction with integrated gallium phosphide photonics from IBM. Congrats. And now to the 4 winners. So the first one is Elias Portoles, gate-defying Josephson junctions in magic angle twisted bilayer graphene. Congratulations. Good job on the poster and the presentation. You can see already from the little cutout of the poster on the slide that it's has a lot of nice plots and drawings. I think I've also seen it in the poster session. Second one is by Alexander Gushinsky, Parallel Grover Algorithm System as Dynamic Systems. Congratulations also to you. The third one, by the way, the order of these winners doesn't play a role. It's just the 4 different judges. By Stefano Barizon, an efficient quantum algorithm for the time evolution of parameterized circuits. And finally, by Rudy Hanna, an in situ fabrication of Josephson junctions with ALD tunnel barrier for transmit qubits. Congratulations. We'll contact you for your details and send you a cash prize. Yeah,
it's important to say that say 2 professors judged half of the post and the other 2 professors the other half, so that there were no like bias between professors choosing the poster of their own postdoc or PhD.
Yeah, of course. And then we also made sure to select the 2 judges from theory backgrounds and 2 judges from experimental backgrounds, which I think you can see here. Yeah, 2 theory posters, 2 experimental posters. And that's what happens. Okay, congratulations to the winners. I hope you all enjoyed the school. I don't know if we're going to do a next 2022 version, or maybe we'll hand over all the files that we have to someone else to do it. But yeah, this was a lot of fun, and I enjoyed all the talks a lot. I certainly learned a lot, and I think that goes for all of us. So yes,
if you are interested, if you're a student at EPFL or ETH Zurich and are interested in running this sort of conference next year or in the post-COVID world in person even, please get in contact with us and we'll talk to you.
It was a lot of fun, and we already went through a lot of the loops, so we can tell you how to do it. Yeah, get in contact. And yes, that's it from us. Enjoy your evening and enjoy your weekend, and good luck with all your very interesting and fantastic research. There's a bunch of stuff in the chat.